Damian has worked on many things, and among them he's an expert of quantum field theory and renormalization, and among these things, properties of theories of gravity with higher curvature terms, where ghosts appear. And recently has developed a method and a prescription for treating these ghosts. And he's going to tell us about that today. Damiano,
thank you very much. Yes, so this is a method to convert the would-be ghosts into something completely new that doesn't destroy unitarity, actually, that is compatible with unitarity. And that is the concept of fake particle. So we'll see what it means. And I will start by giving you a glimpse of what it does mean. So first of all, the idea of fake particle, which I call fakeon, allows us to make sense of higher derivative theories. But it's very, very general, actually. It can be applied also to non-higher derivative theories. And indeed, it amounts to a quantization prescription for the poles of the propagators, different alternative, if you want, to the Feynman I epsilon. So if you want, the Feynman I epsilon tells you what a particle is. And however, if you have the wrong sign in front of the propagator, the Feynman I epsilon gives you a ghost, which is a -1 particle. And the fakeon is a 0 particle, something like that. And this idea leads to an essentially unique theory of quantum gravity that is just within the same approach as you would have for the standard model, as we do have for the standard model. So quantum field theory, a perturbative quantum field theory where you can compute Feynman diagrams. And then you have a scattering theory, essentially. And then the problem, and I will describe, which is what I'm studying now and also interacting with Eugenio, is to convert this into something that can be useful to make predictions, for example, in cosmology, or something more closer to what we may observe, because high energy experiments in quantum gravity are not really easy.
So there are other approaches, right? I mean, like there was one sort of causal propagator approach. I don't know if you're familiar with from Zurich, and that was supposed to make theories even finite, not only renormalizable. Is there any reason to any relation with what you're doing in that?
So you are talking about a causal propagator. So I may take this chance to anticipate that in this approach, the only price is precisely causality.
Nice.
So you will have renormalizability, unitarity, stability. You will have positive bounded energy, bounded from below. But that's the thing you cannot claim up to arbitrarily small distances. So this is the key point.
So this is quite different from that.
Yeah.
And what about asymptotic safety? This is still a Gaussian fixed point that you're doing?
Asymptotic safety here is still open, the question mark. But I will comment that this theory is perturbative in the same sense as the standard model is, so for elementary phenomena, of course, because black holes are up to an unbelievably high energy. We will see the value of that energy. And beyond that energy, the theory could be asymptotically safe or not, but this is still open. Certainly it is not asymptotically free. That I can.
It's not asymptotically free.
It is not asymptotically free.
But so it's really the Gaussian fixed point that you're looking at, right? I mean, but it be around in Gaussian space.
Yes. So, it's the talk is planned precisely to have an interaction, continuous interaction. So I will briefly introduce the new ideas and then move to predictions. And I will discuss the classical limit, because the classical limit bears some unexpected features. There are some non-perturbative aspects that remind you that the origin of everything is quantum field theory. Then we'll see the Friedmann-Roberts-Walker solution, some funny effect on the Hubble constant. But basically, the new concept is what? the fakeon is what? A purely virtual quantum. Normally quanta can be virtual or real. If they are on shell, they can be real. If they are not on shell, they are certainly virtual. There cannot be a quantum that's always real. That would be classical physics, but classical physics is just an approximation. But can there be a quantum that's only virtual, that can never be real? And that is the idea. So basically, this investigation was trying to find a spot in quantum field theory that was not considered carefully enough and look for something that was missed, room for some new idea. It simulates a physical particle in many situations, but it does not belong to the asymptotic spectrum, so it's purely virtual. It can never become real. And just to prepare you, think of the Faddeev-Popov ghosts or the longitudinal and temporal modes of gauge fields. You have extra degrees of freedom when you want to quantize gauge theories, yet you keep them because you want a local theory in good Feynman rules, and then you project them away at the end. And you know, because you have a symmetry principle that protects you, that this is fine with unitarity. So the idea is something similar. The fakeon is something extra that needs to be projected away at the end, but it is not in the physical space, and it is around in the intermediate steps just to keep everything local, because otherwise when you make the true projection, you will find something funny, and we'll see the main properties of this. So it's something that does not follow from a gauge principle, and indeed, when you eliminate it, when you project it, it does not disappear everywhere like the Faddeev-Popov ghosts, but it leaves a remnant, which is the violation of causality at very small distances. So basically the problem of quantum gravity from the approach of high energy physics is to make it renormalizable and unitary at the same time. Because the Einstein theory is not renormalizable, but it is unitary. And if you want, you can consider a higher derivative theory, like this one, where you have a cosmological constant, the Hilbert term, y squared and r squared, and that is known to be renormalizable. That's the Stella theory, when you quantize the poles of the propagators in the usual Feynman way, but then one is a ghost. Because the higher derivative propagator has a better behavior at high energies, it decreases more rapidly, that's good for renormalization. But if you decompose it in partial fractioning, you have a dangerous minus sign. You necessarily need a difference. And then this leads to the ghost. So basically, unitarity is a statement that the S matrix should be unitary. And if you want, you can introduce a completeness relation to describe it by means of relations among amplitudes. Well, the point is that when you have the higher derivative theory, due to these minus signs, you don't have a completeness relation like that. You don't have a unitarity equation. You have a pseudo-unitarity equation, which looks like this. Namely, some states in the middle need a minus one. And then you cannot interpret it as a unitarity condition. So to solve this problem, you need something radically new. And here is the basic idea. So take the propagator. This is an unprescribed propagator. Before the prescription, I put both signs because I want to tell you what happens when both cases are considered. So take Feynman, the Feynman prescription. Then what you get is this, namely an object which has an imaginary part, and the imaginary part is what's real. So it's curious in the name. What's imaginary is what's real, and what's real is what's imaginary. So the propagator has an imaginary part written like this, and the imaginary part of the propagator is the on-shell particle, so the real particle. So I should put an I to make it correspond to the real part. The point is that if you have the right sign in front, you have the right sign in front of the delta function. That's a particle. If you have the wrong sign, that's a -1 particle. It's like saying that you have negative probabilities, negative norms. You can rephrase it in many ways, but it never goes away. Well, the idea should be to take a zero particle, namely have no on-shell contribution. That's the idea for a virtual quantum. And then leads you to consider something like that, which is the principal value of this propagator. But I wrote here beware, because if you use the principal value inside Feynman diagrams, you find a very, very bad behaviors, and that's the reason why it has not been considered so far. Actually, you find that the purely virtual quantum cannot really define from its classical limit because it's purely quantum. So I need to explain to you what to do inside Feynman diagrams. And then we will understand also the classical limit. But from a God-given classical limit, you will not be able to infer. So I can anticipate that the classical limit will be this, the principal value. But there are many things which have the same classical limit. And this is found only if you study directly loop diagrams. So the simplest loop diagram is the bubble diagram. Let's concentrate on that. You can compute it, that's in all textbooks, and you find that as a function of the external energy, which is complexified, in the complex plane, you find two cuts. One branch cut and the cut, one branch point and the cut, and the other one. There is, where you have a singularity, normally you have some physics, something interesting for physics. And that's the threshold above which the two virtual quanta become real. And you can associate those branch and the branch cuts to the cross-section for the production of those virtual particles which become real. That's the unitarity condition. You can rewrite it as the optical theorem, and it tells you that the imaginary part of the diagram is equal to a forward scattering cross-section. Good. So if you want something that never becomes real, this imaginary part of this cross-section should be zero. So Feynman tells you that if you want to compute your diagram above the threshold, you can compute it in the Euclidean, and then you Wick rotate, and that means that you get above the threshold from above, from the upper half plane. If you compute it from the lower half plane, you get a complex conjugate amplitude. Both are necessary because you see the unitarity condition involves an amplitude and a complex conjugate amplitude. So the Feynman prescription is analytic. You can compute on the imaginary axis, which is the Euclidean region, and then you Wick rotate. But then you find a discontinuity, because if you compute it from above or from below, you have different results. A discontinuity between above and below is the imaginary part. The imaginary part is non-zero. By unitarity, it is related to this production cross-section, which means you produce something. The fakeon comes from a different prescription to do the Feynman loop integral, and it amounts to a complicated procedure that I will not review here, but basically you have to deform the integration on the loop energy and then complexify also the loop space momenta and deform them as well, and you find that there is a unique procedure. But then there is a mathematical theorem that tells you that the final answer is very, very simple. So let me just give you the final answer. The final answer is just the average of the two analytic continuations. Just like that.
So you get a propagator. Does it satisfy the same equation as the Feynman diagram, a Feynman propagator, or does it satisfy a different equation because you added another two?
The propagator satisfies the same equation. It's a different prescription for the same propagator. And so you have an operation that is the average, the arithmetic average of two analytic continuations, and the sum of two analytic functions is analytic, but it is not analytically related to the original function that you find in the Euclidean region. So if you start from the Euclidean region, you have a unique procedure to go beyond the threshold, a la Feynman, and you need a unique procedure to go beyond the threshold, a la Fake. But with the Feynman procedure, you can also go backwards, because it's analytic. This is a non-analytic operation, unambiguous but not analytic, that does not allow you to go backwards. And because it is this average, you don't have any imaginary part. You don't have this discontinuity. You have this cross-section for the production of those particles equal to 0. And that means that those virtual quanta remain virtual.
So if I just were to work in Euclidean space only, then usually one knows that that propagator, one can just say goes to 0 if the 2 points go to infinity and there is a. So if I were in Euclidean space, how would I select this propagator? What boundary conditions do I have to choose to?
So in the Euclidean framework, the theory is exactly the same. That's as you would have with the Feynman prescription. The Wick rotation, however, so you start from the same Euclidean amplitude or the same Euclidean theory, and then you start the Wick rotation. Wick rotation is completed in a different way here. In the usual case, it's completed analytically. So you just rotate. In this case, I call it a non-analytic Wick rotation because what you get here must be continued from both sides, and you have to circumvent the branch cut and go on from that for all thresholds you find on your way.
So is there a geometrical meaning to this Wick rotation then? I mean, because normal Wick rotation in space-time diagram would really say that T goes to IT and the metric goes to something. So here, and that is an analytic procedure. So here, is there a geometrical meaning to Wick rotation, or is it implemented only on the propagator and does not have any geometrical transformations?
Yeah, this is the part that I skipped. But basically, what happens is that if you the geometrical meaning.
Anytime it is diverting you too much, just we can skip it and come back at the end of the talk.
Yes, let me see if I can say a couple of words to give you a glimpse of what happens, because basically you will find that you see that you have this width there, and you have to take it to 0. Now, work with that different from 0 to start with, because it has to be different from 0. Then you will not find branch cuts. You will find an extended region. And then you have to make all sorts of operations to deform contours, because if you go inside that region directly, analyticity is broken, Lorentz invariance is broken, that's spurious. But when epsilon goes to 0, this shrinks. So Feynman would say, calculate here, and then take the limit from above. I say, calculate inside, and then take the limit. That's the symmetric thing to do. You calculate inside, the result inside that region violates analyticity and Lorentz invariance. Then take the limit. In the limit, you recover analyticity and Lorentz invariance. And you get precisely this. So that's how you have to do the Wick rotation. You have to do the Wick rotation for epsilon different from 0. And then you will see that there is an obstacle there, because you don't have branch cuts. You really have extended regions. Then you have 3 possibilities: from above, from below, from inside. That's the new thing.
So this is a prescription of Wick rotation on the propagator.
Yeah.
But rather than on space-time geometry. And you're saying that, if I understood it correctly, that it's not clear or it's not obvious what the procedure is in terms of space-time geometry. which is fine.
No, that is one of the outcomes. Not only it's not clear what you do in terms of space and time, but I will. One of the outcomes will be that you have really to abandon that kind of approach, because from a certain point on, you will see that everything lives in momentum space, and you will say, okay, energy and momentum are dual to space and time. You will not able to go to arbitrarily high energies that you can do in energy momentum space, but that will not correspond to arbitrarily small distances or intervals of time, because time will cease to have a meaning. And everything here is in momentum space. So the difficulty will be to translate this in coordinate space. And that's why you run into some problems in if you want to describe, for example, cosmology or everything that concerns solutions to the classical field equations, black holes, and so on and so forth, because everything really here. Already in quantum field theory, you can say, standard model, everything you know is very simple in momentum space. But if you want to formulate quantum field theory directly in coordinate space, you can do. It's difficult to renormalize to all orders, to prove theorems, but you have a propagator in coordinate space, you can do it. But the fact that it is much more difficult already gives you the hint that it may not be the right way to continue. And in this approach, quantum gravity is definitely, in this moment, I cannot even tell you what the fakeon prescription is in coordinate space. I cannot even tell you. That's a totally open subject. I can only work in momentum space, and then every time I want to know what happens in coordinate space, do the Fourier transform. With a warning that I will have t and x, but they will cease to make physical meaning below certain distances, because the t, there will be no difference between space, between present, past, and future. It's basically below a certain.
So how do you see this? If you just take this propagator and you transform it to a position space, where do you see the feature of the new scale that you are introducing? What is it that goes wrong in the position space propagator?
It's we will see this in detail. It's the fact that if you use that propagator, you will have to anticipate a little bit of future if you want to predict the future, and that little bit is parameterized by the mass, 1 over the mass of this fake thing.
Okay, just one last question. No, this is extremely useful because I heard previous talk and I got a very vague idea, but now this is very good. So you're going to use Feynman propagator for ordinary particles, but you're introducing an additional particle, or are we replacing all Feynman particles for all particles? So for all particles, even those which are real, with the new one.
You can do basically whatever you want. So you have you can call it a quantum field theory particles and fakons. There is only one warning: you cannot fakonize anything massless, because otherwise you violate causality at large. But as long as you have a mass, and it should be heavy, because otherwise you have contradiction with experiments. So I will comment maybe, if I have time towards the end, that the Higgs boson is still open, whether it could be fake or not. But in principle, you can do that.
Yeah, and just to add to what I was going to say, but in the beginning, you had as motivation this higher curvature or higher derivative gravity, where you have higher time derivatives. So there, it's the statement you were making that you need a little bit of future. It's not that surprising, because you already have a theory where there are higher time derivatives in the Lagrangian, which require more initial conditions, even classically.
But that's different from.
But it's true that even if you take a normal scalar, you can fakonize it, and then you have the violation of causality.
So I think it is different, at least. Right?
And
yeah. I mean, it's true that you need more initial data, but if you give more initial data, then you can have a well-defined formulation. But here the statement would be that there's really probably not initial value formulation at all for the fakon. Yeah, I think it's good. Actually, so is there a Hilbert space for fakon?
Yes.
So we'll talk about
we'll give but I will describe, even in the case of the higher derivatives, I will convert them to normal derivative theories, just to make it more clear, because Well, if you're familiar with the bubble diagram, you may have seen this kind of integral here. Just to tell you that I'm talking about something that can be written and is under control. This is in using Feynman parameters, what you get for the bubble diagram in the Feynman prescription. The only difference, you get no I epsilon here, but you get a square. So you break. You have one analytic function below the threshold, a second analytic function above the threshold. But the two are not analytically connected because the imaginary part in the Feynman case is 0 below the threshold, and then there is the square root. That's the production cross-section for the virtual particles that become real.
Instead, it's square, right? Because it's log up square, and then there's 1/2 in front, so it just cancels out. No?
They are the same below the threshold, where the argument here is real and positive, but above the threshold, when the argument becomes negative.
Right.
So in case of quantum gravity, let's go back to this theory, and let me also add the standard model, because I will then make calculations with everything inside. But basically, let me add some. You see here there are many constants. The cosmological constant, I put a zeta here, which has to be positive, and alpha here, which has to be positive, xi here, which has to be positive. There is one redundant constant. That's because the high energy limit will require some normalization, and the low energy limit a different normalization. So just bear in mind that there is one constant more than you need, but that's fine. If you convert the square here into something like that with an extra field, and you do the same with that, you can eliminate the higher derivatives. Then let me tell you what happens. The action can be written as a sum of terms with no higher derivatives. One is the standard model part, so forget it. One is the Hilbert term. I kill for the moment the cosmological constant, just to keep it simple. The Hilbert term is fine. Then you have a scalar field, which is the Starobinski part. That's fine also, has very good potential. It has the right coefficient with the right sign. And then you have the rest. You need a spin 2, you see. From the Ricci squared term, you need a chi-mu nu, which is a symmetric tensor with a complicated action. Okay, it's complicated, but let's get to the key part. If you expand it in chi, forget about the interactions, forget about the non-minimal terms, what you get is a Pauli field. So it's a massive spin 2, Pauli fields, covariantized, but with the wrong sign. And that's it. That's what you have to quantize as a fakeon. If you do that, you have both renormalizability and unitarity, because, oh, by the way, I didn't focus on this, but renormalizability will not be destroyed by the new prescription, because the Euclidean theory is always the same. Renormalization basically knows about real parts, not imaginary parts. And the Euclidean theory knows about the real part, because that's real. And if you make an average continuation of a convergent function, it will always be convergent. So once you renormalize the theory in the Euclidean, you can rotate analytically or not analytically, as I told you, making an average of two analytic functions, but if they are already convergent, they are convergent. The result will converge. And then to come back to one of your questions before, what about phi? Phi, for example, is very normal scalar. Would that be necessarily physical? It could be fake also. So you have two choices, and only experiments will decide, because there is a difference at the observative level between the two possibilities. So basically now, quantum gravity is described by triplet. One is the fluctuation around flat space, so let's say the graviton. One is a massive scalar, and one is which could be a fake, and one is a massive spin 2, which is necessarily fake. The masses are related to the parameters of the various coefficients. Just to convince you that you can treat this as you would with a standard model, for if you want to do an high energy physics, you can, for example, resum the bubble diagrams for the graviton self energy. Let's say geometric series, you find the width of the fakeon. Not surprisingly, it is negative. Actually, there is a theorem that tells you that the sign of the width coincides with the sign of the pole of the propagator. So chi has the wrong sign, and therefore the interkinetic part, by unitarity, because now we have unitarity, you can show that the width is necessarily negative, and that means a violation of causality. Let's go into this more detail.
So it is essential to have phi, is it? I mean,
Yes, exactly. I cannot get rid of that. It's essential. Even if it looks innocuous, without it, I cannot make the theory work.
so that's another aspect in which it is different from the Papagos or something.
Yeah. And well, just to start talking about the violation of microcausality, if you have a negative gamma, if you take a bright Wigner and take the Fourier transform, well, first of all, normally you have a damping factor. With a positive gamma, it's still damping, because the Fourier transform of an L2 function will always be L2. It cannot blow up. And the reason is that this factor is always damping because the theta function in front switches sign. The argument of the theta function is gamma t. I wrote it gamma t to say that when gamma is negative, it sees the future. So if you use it as a green function to study the response from a source, you get, for gamma negative, an integral from t to plus infinity, which means that you need to know the source in the future to predict the future. But actually, since this green function is damped or very, very rapidly oscillating, now we will come to numbers, but this mass could be 10 to the 12 GeV, 10 to the 14 GeV, and that means that the time involved here could be 10 to the minus 36 seconds. Okay, something unmeasurable. So far we have been measuring time just up to 10 to the minus 17 with laser pulses. That's the best we have. So from the experimental point of view, below 10 to the minus 17 there could be no time at all. According to this theory, there is time up to, however, 10 to the minus 36 possible. But this is a free parameter now, yet. So I'm throwing some numbers because we'll discuss later, but it cannot be very precise on how much this the fakeon mass is. Now, an interesting thing is that the violation of causality is also in the classical limit. So let's see what happens in the classical limit.
Are you looking at this scalar field for concreteness? So this is the mass of the scalar field.
Oh yeah, no, this is actually no. I'm using phi. No, forget. This is anything.
Okay.
Yeah, no, it's not the same.
So any mass will have. So basically, the causality of violation will be dictated by the lowest mass of the fakeons.
Yes. So in the case of the level of Fock spaces, you have to remember that there is this new prescription, which is a new way to quantize those objects. But then you have also a projection, because those, like the Fadeev-Popov-Gauss case, in this case they are similar. If you have in a gauge theory Fadeev-Popov-Gauss, you do not consider correlation functions where you have scattering of Fadeev-Popov-Gauss. You just project them out, and you have unitarity only in a subspace. So basically you have a vacuum state, and you have a Fock space that you can build by acting with creation operators of all types. Let's say you have physical particles and you have fakeons. That's the total Fock space, but that's not a physical space. In the total Fock space, the Hamiltonian, the free Hamiltonian, is not even bounded from below. The subspace, the projected Fock space, is the one you obtain by acting on the vacuum only with the creation operators of the physical particles, those that you quantize as physical. In this subspace, the free Hamiltonian is bounded from below. And you have stability, namely you have only scattering between initial particles that have positive energies in total and individually, and final particles that have positive energies in total and individually.
But from this description, it looks like fakeons and this is the free field theory. Therefore, all these creation and annihilation operators commute for different operators.
Yes.
And then it looked almost like the fakeon Hilbert space is again built out of positive frequency, part of some solutions. Is that correct?
Yes.
You've already gone to the momentum space, but if I were to start at the free level from space-time and then go to the then are they just satisfying the wave equation in physical space or what?
Yes.
Yeah. So, and then the Hilbert space is a standard Hilbert space for the. On the one hand, it looks like it's a standard Hilbert space for massive particles. On the other hand, it cannot be, because if I knew the standard Hilbert space, I can calculate the final propagator by expectation values of the operators, suitably ordered operators, and your propagator is different.
Yeah.
So therefore, I would think that the Hilbert space is not the standard Hilbert space. So, what is the Hilbert space for the fakons?
Yes, so I agree with that, because that comes from with the fact that if you want to use this approach to build non-trivial interactions and Feynman diagrams, then when you have to compute them, you need to know the prescription that I gave you before. So that is probably, that's also something that needs to be at the moment translated from the approach where I know how to define it into this one. And since already some people have raised this question, I will have to look at it in detail. Although my approach has always been the functional integral and everything in that realm, so that's where I clarify everything so far.
I mean, just usually, the question is here really, it's a Hilbert space, the positive definitely in the product, right?
Yes, yes.
Yeah, so there's a complex structure.
Yeah.
Right? So the usual complex structure is chosen by pointer invariant, and then it gives you causal propagators and everything. So he's choosing a complex structure which is not like that. So I think we should be able to find out what that complex structure is, which has
there should be
properties, and that I think is the kind of crux. I mean, for us, I mean, you are very facile with all the detailed calculation, but we are not. So for us to understand the conceptual structure, that is what is happening.
I agree.
I think it is a very interesting problem.
Yes.
I don't know if Damiano is going to show this, but he has worked out some very simple examples, like take simply a harmonic oscillator or even a free particle, where you put higher derivatives in time, and you ask what's the quantization of this single degree of freedom and what's the Hilbert space. And there's something interesting that appears, that is, if you take a harmonic oscillator and you make this prescription, you find that you can describe it with an effective Hamiltonian with a different frequency, which would mean that the as you're saying, the vacuum would be defined by a complex structure that is not the naive that you would have guessed by just looking at the naive at the Hamiltonian start with, but there's a new one with a different.
Which, when interpreted in the original language, would give you this non-causal propagation. Something.
Exactly.
That's very interesting.
So, so it's crucial that you have to project those things away, because in the full space you don't have any of the good properties. That's obvious. Even if you take a scattering of a Faddeev of ghosts, you wouldn't never have unitarity. So just to give you briefly the details, how is the projection made? Formally, it's very, very simple. At the computational level, it's complicated because you have to compute Feynman diagrams with the prescription I gave you before. But formally, in the functional integral approach, you just don't put sources for the fake particles. Or in the, the gamma functional, source equals 0 means you solve the field equation for the fake and you insert the solution back. This is very formal because you know how to solve this equation, and this is a sum of diagrams. You solve it with the prescription we saw before. But in the classical limit, everything simplifies. You have to do the same, but in the classical limit, let's see what happens. So we have a taste of some interesting new problems. Because what I'm telling you now is that the classical action I started with is not a classical action. The classical action, the classical limit of the quantum theory will be a different classical action. Why? It's like a gauge-fixed classical action. You don't take it seriously. There are Faddeev of ghosts. have to get rid of them, even classically, of course, because the classical action is F mu squared. Here there are the fakeons. Even classically, you have to get rid of them. So basically, you have this triplet. You have 3 field equations, and you have to solve the ones for the fakeon, or both these, if both are fakeons, with what boundary condition? No boundary condition. You have no degree of freedom. It's fake. It's frozen. Everything is already decided. By what? It's decided by the prescription I gave you. The prescription is very complicated, as we saw in Feynman diagrams, but now we are not in Feynman diagrams, we are in the classical limit. And in the classical limit, it is just the principal value.
Are you working in Euclidean sequentiation in this classical limit business?
No, there is nothing Euclidean here.
Okay.
This is Minkowski. So now you know that the prescription is very simple, the classical limit, but yet it's only known perturbatively because everything comes from perturbative quantum field theory. I claim I have a perturbative theory of quantum gravity. It's not that I can claim I can solve it non-perturbatively. And so you see this is in flat space basically. And still the projection is very simple formally, but then it's difficult because it's only known perturbative. Let me give you the example that Eugenio already mentioned, and then we will see something that happens in the Friedman-Robertson work case. So basically, take a non-relativistic Lagrangian, mv squared divided by 2 plus an external force. So forget the higher derivatives, and it's the normal case. Now, you add this higher derivative terms. The field equation is like this, the equation of motion. You see that you factorize a 4th order operator, kinetic operator, into the product of 2 order 2 operators. You have, this is the extra degree of freedom if you want. You have to throw it to the right hand side with the fakeon prescription. Here the result is unique, and that's what you get. Instead of F equal MA, you have MA equal to some average, where this is that, the Fourier transform. You see an oscillating function, but you pick past and future. So that's the violation of micro-causality. When tau goes to 0, this tau goes to 0, this is a delta function, and you get F equal MA. But when tau is not 0, this tau should be small, so this is a very rapidly oscillating function, and everything averages to 0, but in a neighborhood of the present. But the neighborhood contains a little bit of future and a little bit of past. So that's violation of microcausality. That's very simple because this is a non-interacting theory. When it's interacting, something interesting happens.
Can I
Yes,
about this one?
sure.
This is the part that I found really illustrative of the method, so I want to use the time to ask some questions on this. Okay, so when tau is 0, this is the standard theory, and when tau is small, you can check that the limit goes back to F equal MA. Now, the question is, what is the prescription capturing when tau is finite, or maybe smaller? So, is it fair to characterize it in this way? If I take that theory, it has higher derivatives, so to solve it, I could just say, this is a differential equation with 4 time derivatives. I have to give 3 initial conditions, and I find one classical solution. And now in this space of classical solutions, you're identifying a class of classical solutions that have some special property. The F of t is a protocol is given, you already know it before asking which classical solution, which class of classical solutions you're looking for. And it's a class of classical solutions that depend on F of t with some requirement of stability or some requirement that is specific to your prescription.
Actually, this is the prescription that comes from quantum field theory. And I do not introduce physical principles here. I do not introduce any guiding principle. I just learn it from the fact that that's the only way to make a theory renormalizable and unitary at the same time. But this comment is very good because it allows me to stress this point, which is I'm very strong on this. Don't be fooled by physical principles. We do not know down there what the physical principles are. We do not know, and that's why you have to be ready to everything. So maybe you can say that this is a little bit technical, because it comes from that prescription. That's the only thing that works in Feynman diagrams, so on and so forth. And then you see, once you do this trick, you have a definite answer. This is a two-derivative equation. Now you have two initial conditions you can choose. You cannot here introduce boundary conditions, because that's it. I'm telling you what the green function for this pole is. So the pole disappeared now. There is no freedom. It's not a degree of freedom because it's a fake degree of freedom. But for example, it's non-causal because it involves the future. So certainly it is not something that you can get from by imposing causality or something like that, some physical principle.
So what is the fakeon here?
That would be the pole of this, which is the extra degree of freedom, which disappears because of the prescription, which in this case is the principal value, and that freezes the degree of freedom and reduces a local unprojected fourth order equation of motion into a non-local projected second order.
But I mean, X was kind of a continuous degree of freedom. It's a fakeon, and the Hilbert space was L2 of R. So for this fakeon, I mean, I understand that pole and so on, which is your way you think. But can I think of a Hilbert space of states for the fakeon here in this case?
Yes. Yes.
So what would be the Hilbert space of states? It's square integral function of what? Of X dot or X double dot?
Yes, okay, that I don't have it in the slides, I have it in the paper. You can write it as, you can introduce the creation operators for both degrees of freedom, and then the physical subspace will be the one where you act on the vacuum only with the creation operators of one of the two, the physical one, and then you drop the other one.
So this new degree of freedom I don't identify with anything else with X, it's just a new degree of freedom. So, I mean, from an initial value point of view, as we were saying before, if you did not have, if tau were equal to 0, then the initial, I just need X and X dot at the initial, and then I get. But now I also need X dot and X double dot probably.
Here,
yeah,
you need that, but that is unprojected. So that's the extent. Right? Here you just need X dot, because the right-hand side is given now.
Right.
So you have...
right, but in the unprojected case, I understand the fakeon thing. So, but somehow it's not clear to me that there is any identification at all between X double dot and the fakeon. Is that correct?
Yes, no, X double dot is not...
Yeah, so the fakeon is just another thing, which is...
the fakeon is
unrelated to X.
Is described by the two initial conditions you lose. That's gone. That's why down there is no fakeon anymore. Or actually, there is a remnant.
I understand the project. After you project, there is no fakeon. Then.
Here.
Yeah.
Then it is the pole of. Okay, I use the
pole. But I mean, can I think in terms of, normally the square integral function of X now is the total Hilbert, the fakeon Hilbert space. It's just independent, or is it related with X?
It's I would say independent, because if you can with an extra field remove this higher derivatives, and you will have a Lagrangian, which is the difference of two kinetic terms. One has the wrong sign as usual, and the Hamiltonian as well.
The wrong sign is the
yeah, exactly. So you have in the Hamiltonian a contribution a dagger with the wrong sign. That's
the last thing is that even though it's non-causal, but it's not strictly non-causal in the sense that what you need to know for future time is really the external force. You don't need to know X at a future time. It's not that. Right?
That's correct.
So it's really, in that sense, it's a perfectly well-defined.
That's correct.
Yeah.
So here indeed you could save the date like that. But in the next transparency, instead I put self-interactions there. And that's where you have pain. Because if you put, let's say, x to the fourth, let me go quickly on this, you will have that. And then you have to use an iterative procedure to make the projection. I want just to give a taste of what happens, because since the true theory is the projected one, it's not that, you have to go there, but the theory vindicates itself by making life hard, because it forces you to remind that everything comes from quantum field theory. In quantum field theory you have infinite series, asymptotic expansions. Try and do iteratively this projection, and you will find an equation which is x dot dot equal to an infinite sum, and the effective Lagrangian or Hamiltonian or whatever you want, with no higher derivatives at this point, yet it is an infinite sum. And okay, you say, who is scared by infinite sums? Well, the point is that the coefficients grow like n factorial to the fourth. So the projected field equations, the equation is an asymptotic expansion, not the solution, as you find in quantum field theory. Yet you know that asymptotic expansions are useful even in particle physics, because as long as you have one expansion parameter, which is smaller than 1, let's say 1/10, then the first 10 or 9 orders capture the solution very, very well. And then from the 10th order onwards, they become crazy. So if you have a convergent expansion, that's convergent. But bear in mind that it normally converges so slowly that asymptotic expansions are better for physics in most cases. But if you have an expansion parameter that's not an expansion parameter, namely equal to 1, and that's something you happen to have close to the Big Bang, then it's hard, okay? Because it's like saying that I cannot even, with my approach, with this theory, give you the field equations. In that case, I cannot give you the classical field equations, for which I would need to solve quantum gravity non-perturbatively. But because everything is understood perturbatively here, I run into this asymptotic expansion, which give you little information to none information, actually, when the expansion parameter is not there. But if you have an expansion parameter, the Newton constant, then it's okay. In the Friedman-Robinson-Walker case, the expansion parameter is factorized and disappears. But let me tell you what happens, because it describes something interesting here.
So what do you do in this case? In this case, you first go to the quantum, you don't look at full quantum gravity here, is that correct? You are just looking at a truncated theory from the beginning?
Exactly. So here I'm taking I would like to understand the classical limit of the quantum gravity. And basically the classical limit is the projection of that higher derivative Lagrange. Here it's simple because you know y squared is 0. The term with y squared is absent, so I would have to study the projected version of this higher derivative Lagrange, similar to what we did for classical mechanics, higher derivative classical mechanics in the previous slides.
But you're not looking at that full Lagrangian. You're looking at that Lagrangian as truncated to homogeneous isotropic sector. Is that correct?
Yes, yes. For the moment, for the background only, yes. No.
And this one, so in this sector is fine. There's no cos this sector. So you're going to apply the procedure.
Exactly. There is no, the thing that would be a ghost is not there. But remember that I have, even if phi is not, no chance to make it as a ghost, I could still study the possibility that it is fake. So this is maybe an exercise if you want. I don't claim that I have arguments to claim that phi is fake in nature. But let's assume it is. And then you have an interesting problem, how to make the projection in this, and what is the projected classical theory. If you write the equation, you will see that they do factorize, as before. you have rho and p, or rho plus p on the right hand sides, and the kinetic part, the left hand side is the usual one with two operators which are written here. So the projection would amount to take this and throw it to the right hand side with the fakeon prescription. Well, if you do that, you will find equations that look more similar to the usual ones, but there, to the right hand side, you have averaged sources, and you can also define really literally some average sources and make them look exactly like the usual ones. But remember that in after the Big Bang, you need to solve these consistently. You don't have an external rho and p and calculate A. You have to solve them all together, and that causes some trouble because the average depends on A. But there are some lucky cases I just mentioned, if in case they might.
So let me just understand the last step. I mean, normally when I got this treatment of the Raychaudhuri equation, and I also have conservation equations for the.
Oh yeah, it's a consequence of those two.
But the point is, yeah, but it's a consequence of the other two. But here also is a
Yes,
consequence.
yes. And it holds for both rho and p and rho tilde and p tilde. I could replace the two equations with the continuity one and one of the two, because actually that's what I use in this exact solution. So normally you have this infinite series with the asymptotic expansion. For example, with dust, that's what you get. I cannot find the exact projected solution with dust. But you know, also in quantum field theory, you have some lucky situations where you resum the perturbative expansion to all orders. Anomalies, the renormalization group flow, the width we saw previously because it's just a geometric series. Here the case you can solve exactly is radiation and vacuum energy, and actually the combination of the two. There is a reason for that. They are the two cases where either this is 0 or that is 0. And the average of 0 is 0. Perturbatively, non-perturbative, that's the only information I'm using. And even the average of a constant is 0, so if you combine the two, this is a state equation of state for radiation combined with vacuum energy, then you can solve it and you find a little departure. That's the only correction with respect to the solution you find with Einstein only. The higher derivative term gives only a correction, which is a relation between three constants that normally are just two, because the second and the third are identified. Here there is a funny relation, and then you have all the formulas you wish. Okay. No, this is not here. Okay. Let me see. It's over. Oh, so what can I say now? Yes, let me start from last comment from this very quickly. Some people ask me, can the violation of microcausality be amplified? The answer is no, but it's not obvious, because if I tell you that causality is violated at small distances, some people can tell me, okay, but if I change reference frame, it's violated at large distances. Yes, but this principal value gives a Yukawa green function, one for the past and a mirrored one for the future. So the violation of causality is because you have a Yukawa also for the future light cone, and nothing from outside the light cones. But it's a Yukawa, so it's short range, which means that if you really wanted to amplify the violation of microcausality by switching to a different Lorentz frame, you put the numbers in, you have to go to such a high velocity that we simply never reach that. So I just give you, with not many details, the confirmation that there is no contradiction, immediate contradiction with data as far as causality is concerned. You have to put numbers in. For example, you have to know that the shortest amount of time that we have ever measured directly from laser pulses is 10 to the minus 17 seconds. The shortest distance is 10 to the minus 17 centimeters in our rest frame. So you see there are 10 orders of magnitude which means that time is much less accurately measured than space, not surprising. The point is that when you change your reference frame, you mix space and time, and the worst accuracy prevails. So if you go to a different Lorentz frame, normally you will have the worst precision for both time and space, and then that makes everything bad. But let me show you some case where another case where I can exactly resum the perturbative expansion, and that's the case of the Hubble constant, where it is constant. And there, miraculously, the violation of microcausality disappears. So basically, if you take this operator sigma, which is the D'Alembertian of a scalar plus m squared, with h equal constant, and you invert it with a fakeon prescription, you will find that for positive Hubble constant, only the past contributes. The green function will receive no contribution after the resummation of this piece, the powers of h. If h is positive, only the past contributes. If h were a negative, only the future will contribute.
What's the mechanism and why the limit h to 0 doesn't give us the result that you showed us before?
So the mechanism is that if you don't have this, and you invert this with a principal value, you have two poles in the complex plane, and you integrate in between the two, because that's the principal value. When h is positive, the two poles are both up or both down. I don't remember which is the case. And therefore, you just have this result. And you can ask, why is the h equals 0 limit not giving There is a trifurcation basically here that remembers again that this comes from quantum field theory. Normally you don't have this kind of effect, but remember that here, or maybe I did not emphasize it too much. I violate causality, and that is the physical thing, but I violate analyticity also, because of that operation which was non-analytic. And the fact that I violate non-analyticity allows you to get this kind of bifurcation or trifurcation. Basically, it's like saying that in quantum field theory I can choose what I observe. And the result of the observation depends on what I choose to be. In the classical limit I cannot. Well, the classical limit here has a remnant of a choice, but it picks one only. Because in any other case, if I took any other possibility and integrate in between the two poles once they move, I will get something absurd. That's the unique. I understand that I'm not giving you details enough, but time is over, so maybe in that case we can continue. Here I just want to give you a glimpse of what new features you have. Even if, by miracle, you recover causality, that doesn't mean it's over, because it's true that only the past contributes. But since everything comes from quantum field theory, you have contributions from the infinite past, and you don't know the source in the infinite past. Because if you have a problem in an interval of time, you know the Hubble constant is constant only in some interval of time, and it's meaningful to talk about classically an equation of motion in such an interval of time. But the solution depends on the source away from that. So there is an uncertainty here, even if there is no violation of causality, because you don't know that, so you are making an error, a mistake, which is, I mixed up the sequence. So instead of integrating from minus infinity to t, you could only write this, which is wrong. And the error is the rest. Well, the rest, however, is strongly suppressed if you accept that your theory will be predictive not in the entire interval, but you need to renounce predictivity in a small interval, delta t, close to the initial time. So that's how it works. You have a fuzziness relation, if you want, that makes you less predictive than usual. So it's like saying, if you want to predict what happens in 1 second, you need to anticipate what happens in 10 to the minus 36 seconds. That means that what happens in 10 to the minus 36 seconds is out of control. No matter how this the violation of causality can disappear or not, because only the past light contributes, but since it is the infinite past, you still have an uncertainty, or we call it fuzziness. So let me conclude. This is an approach of quantum gravity that is as close as possible to the standard model. It's as conservative as possible. I'm just trying to learn what to do on the bet that quantum gravity can be described by making just one or the smallest step beyond the standard model. And so it is a quantum field theory. Actually, it is a perturbative quantum field theory. You can use Feynman diagram, make calculations as you do the standard model. It's very rigid. I have only 2 new parameters, the 2 masses. And in principle, it predicts everything. I do not accept, for example, the approach by Hawking and other people that tell us that you can live with ghosts if they decay. There is a width. If it decays, it is still in the spectrum. Doesn't mean that it disappears. The muon decays in the standard model. That doesn't mean you throw it away from the spectrum. You can see the muon. And let me comment on this about not asymptotic safety, because I cannot answer that question. I can say from the beta function that it is not asymptotically free, but it's predicted up to an unbelievable edge. Why? Because the expansion parameters, here it's a renormalizable theory. So it's not like the Einstein non-renormalizable theory where you have an expansion in energy divided by the Planck mass. Normally you have an expansion in powers of energy divided by the Planck mass. This is renormalizable, so you have a dimensionless constant. And the fine structure constant is the ratio of the mass of the fakeon and the Planck mass. Or the other one, you have 2 actually. Now, if those masses are smaller than the Planck mass, let's say by some orders of magnitude, this ratio is very small. Alpha is 10 to the minus 14, which is a very perturbative theory, almost free basically. And only the running coupling constant can make it non-perturbative, but the running here is logarithmic because it's a renormalizable theory. And when this running coupling constant becomes equal to 1, that's at this energy. So assume that we are able in our laboratories to multiply the maximum energy we reach by a factor 10 every year. In 20 years we reach the Planck scale, and this one in 1,000 times the life of the universe. So that's how safe the theory is, how predictive, and that's also how scaring it is, because it means that whatever it predicts is at this scales 10 to the 12 GeV in the Planck mass, and then there is an infinite desert with nothing new. Thank you very much.
Thank you, Damiano. We have some time for questions. I do have one about this point you closed on the desert. So you're saying, if I understand correctly, you're saying, suppose that I take the alpha chi, the one that would come from taking seriously the Starobinsky model and saying that coupling constant in front of R square is the one that would fit the data today. So this alpha chi would be in that case 10 to the minus 10 or
Yes,
something
10 to the minus
order.
12 or something, yes.
Uh,
10.
10.
Then you would have 10, I guess, there.
So you would definitely have effects at the scale of the kind. I can look at classical solutions of the theory and do a perturbation theory over the background, assuming that you can generalize your framework to a time-dependent background. That's a separate question. Then you could still do free perturbations of cosmological perturbations, and the question is if there are effects on cosmological perturbations. And then beyond cosmological perturbations, one would have to look at interactions, and one can ask to how many orders your interaction, your perturbative interactions can be trusted. And you're saying, well, the parameter is small, so it's really 10 to the minus 10 is much better than QED or anything else. But before getting there, do you see any effect already in the free theory?
Yes.
Free perturbation.
Actually, I told you the theory is basically free, but that's not true. Interestingly enough, even if the coupling is small, there are so large quantities around that you get normal results from, for example, the gamma that I calculated before, apart from the sign, is equal to the mass of the fakeon times alpha chi. Alpha chi is 10 to the minus 14, but the mass is 10 to the 12 GeV or 14 GeV. And so if you compute those things, that product, you find a width for this fake particle that's comparable to the width of Z boson, W boson, H boson, which makes it, that would be interesting if we could study the peak for these scattering processes. It's only that you have to go to energies that are very large, and then the width will be reasonable, let's say. So I'm looking for effects, similar effects, even in cosmology or fluctuations of CMB, because even if alpha is small, there could be cases where you can say something that could be tested. So before saying that the theory is practically free, I would be cautious. At the same time, you can also understand that all fine-tuning problems here become have a different taste, because there are there's such a huge range of numbers that are big and large around that you cannot really say what is unusual or what is usual or what is natural, what is unnatural. I would not trust. Be very, very conservative and just try and make the computations I can and see what comes out of it.
Yeah, I got lots of questions, but maybe I'll just ask a couple and then we can continue in private. I mean, here you said that no other approach to quantum gravity is as close to standard model, but I think asymptotic safety people object strongly to this. So I just
I gave many talks to them, but they don't object too much because asymptotic safety approach is non-perturbative.
Okay.
And
so you're just leaving that out.
So
I would say it is perturbative. It is perturbative around the non-trivial fixed point.
Yeah.
Everything is perturbative there. I mean, nothing is calculated non-perturbatively, but it is calculated around a non-trivial.
But you understand that it is not really as we do standard model, because standard model could be messy in the ultraviolet or totally different theory. So in that sense, assuming that the ultraviolet fixed point is that the ultraviolet is a fixed point, it's a very strong assumption first, because you don't. That's by definition the region we cannot test. And here I cannot anticipate what will happen, but it could be that the ultraviolet limit makes no sense. But that would be beyond what I call God's energy, just for fun, because it's so high that. But beyond that, you would have to ask the question: is there an ultraviolet fixed point or not? I think that with these numbers around, it becomes a little bit.
I think so. Conceptually, we're saying the same thing.
Yeah.
I agree. I don't know. If we just say that it's not perturbability and that's why this is okay, then I'm fine. But I kind of feel that there is two different things you're saying. One is really at the level of particle physics, kind of model, etc., and the other is sort of foray into black holes cosmology and so on. And in the second part, I don't see, as Eugene said, first of all, you have to understand what it means in a time-dependent background. That's a fundamental thing in cosmology, or black hole backgrounds in black hole physics, etc. And we are not really doing it here. So
No, that's the part that I am considering now. Both things. Black holes that are static, so there you do not see really the violation of microcausality simply because they are static, and when you assume that something is static, you are basically already assuming the future. But that's fine, because still the problem is interesting here. What is a black hole here? And the other thing is the time-dependent background. Yes.
And also, I was not clear about this violation of causality, because you brought in, even in cosmology, you brought in a few slides before, you brought in an extra source, and then you're saying that, well, this source you have to know a little bit before, a little bit after. Right? But, I mean, normally there's no source, so what is what? I mean, there's something in the calculation that you are introducing the source by hand to calculate something.
No, but I agree with you. I agree with you. Actually, normally I don't put it the way I'm going to put it now, because I don't want people to think that I am out of my mind. But actually, the idea of causality is so ill-defined. So I kept this because there is a story behind that. For example, you might know that Dirac did a trick similar at the classical level to the one I explained to you with the runaway solutions. Right. And you have this kind of operator, you invert it, and you have what you call violation of causality by that same thing. This is a little bit of historical notes. And there are the Liebig models, which already brought it up that higher derivatives are related to the violation of microcausality. Actually, the fakeons allowed to formulate the models precisely because they were not formulated in that. Then there is Feynman-Wheeler electrodynamics. That's the closest thing I found with the principal value. But then you violate causality at large, and so they invent some emitter-absorber theory.
Mass is zero.
Yeah, the mass is zero, so that's a real problem. But some people, Bollini and Rocca, studied that propagator at the level of Feynman diagrams. That's very, very bad. They don't notice it, but we'll publish something to make it clear, because everything gets wrong. And there is already a paper with a colleague that I wrote that shows it. Cannot use that in Feynman diagrams. But just to tell you that the most, and here is the key point, because the idea of causality in a deterministic framework makes no sense whatsoever to me. Because if something is deterministic, you can say that the present determines the future, but you can also say that the future determines the present. If deterministic, everything is already written, right? So you have to talk about causality like time ordering, but not the idea of cause is really maybe some philosophical thing, but I don't want.
I disagree. So let's just see. So the question is always comes from initial value formulation. You give me some Cauchy data in some region, and then the solution is determined only in the future domain of dependence of that region, and it's zero outside. That is the notion of causality. And that notion is completely not philosophical. It's a
but if I tell you, for example, that everything that happens here is determined by the future, because our future will have to be certain thing already written. Why can't I say that the future?
You have a well-defined initial value formulation. So if you go into this,
I agree. It's misleading to talk about causes. That's what I'm saying.
Yeah, but there is a precise formulation in terms of initial value formulation. Does your theory admit initial value?
That's why you're saying that basically I'm not violating causality, right? Yeah, that I agree.
So I think we should not.
Yeah, just to comment on this, let me take this. This is a final comment. This is from Toft and Veltman diagrammer. a very good booklet on quantum field theory. They talk about causality in quantum field theory. And that's the only book where they really talk about causality diagrammatically, because if you look at textbooks in quantum field theory, they just do the free propagator and they don't do much. So they comment on the Bogolyubov condition, and which is a certain diagrammatic condition, and then the Lehmann-Zimmermann, which is the requirement that fields commute at space-like separated points. Well, they warn you that there is no agreement on a notion of causality in quantum field theory because both conditions are off-shell. Operators are correlation functions, and when you try and implement them as conditions on the S matrix, that's hard. So in this sense, already with the standard model, quantum field theory told you that maybe causality is not the right physical principle to insist on, and maybe that's also the reason why textbooks leave it aside. But in this case, of theory of quantum gravity, it's true that you don't even have those. And but I agree with you. I normally do not say. I say that I violate causality. But if you want my true opinion, I would not say it that way because I don't think I'm violating anything.
So, but still, okay, that's what my question is. I really would like to understand. So, you have some equations, right? And then, like for example, in the case of the particle, it was when we introduced this extra time derivatives in the equation of motion. In that case, it was clear you're not violating causality because what you have to specify is the source at some time intervals, right? At the start.
However, there is a little thing here that there is an important thing to say because you can say I redefine my external force and so I do not violate causality. But here. But the point is that we have different interactions in the universe, and only gravity brings that average in. So if I compare a gravitational experiment, I see a force that's averaged. But if I do at the same time with the same type of force an electrodynamics experiment, I would see a different force on the right-hand side. By comparison, I can say there is something there. So that's not really enough. That average is something predictive. I cannot reabsorb it into a redefinition of the external force. I can do it here only, because I have written only one equation. But if I did the same for electrodynamics, I wouldn't have the average on the right-hand side. I would have fx. And so it becomes hard to make experiments by comparison, comparing to such two things, but in principle it could be done. So instead of talking about microcausality or violation of microcausality, I just say that you have an awkward, unexpected form of the equations, but still something that has predictive consequences. Because by comparison, the same particle interacting with gravity will have this, but interacting with electrodynamics, there will be a charge somehow you won't have. Yeah.
Let's continue maybe.
So I see that here the formulation and even the discussion of causality is all through the lenses of scattering and in-out, fixed initial state, fixed final state, and now I try to read causality into what scattering amplitudes are. While many of these questions, we often phrase them in terms of I prepare a state, I look at how it evolves, and I compute properties at a certain time, or one would say quantum field theory in informalism. Do you have a version of the prescription that is in, and if not, what is it that needs to be done to do that?
I don't have it right now, but that's one of the major things I want to do because so many people ask me. And so in that case, unitarity will be just unitarity of the evolution. And the question is where, having unitarity, where you have to pay the price. And you're asking me what to do to approach that problem. I'm not ready to answer right now because I'm not familiar with the in approach. I just vaguely studied it in the past, so I need to go through it very carefully, and some students are helping me on that. So I really cannot comment too much about it now, other than say it's definitely something to look into, and it needs to be answered. And among the various things I mentioned, I think that's the most, the thing that can be probably that's most affordable. I would not afford right now, for example, the problem of describing the prescription in coordinate space. I find that very, very hard. But this one is something in between, because you still you need to use coordinates and time. And when you go out, yes. Final comment. I talked about unbelievably high energies, and one can say, how can you predict anything if you don't have time, if you don't have past, present, and future, if nothing makes sense? Well, nothing makes sense in coordinate space again, but in momentum space, it's fine up to infinite energies. That's why you really see that quantum field theory, well, invariance and choice of reference frame and framework maybe is very nice, but yeah, it breaks all ideas you may have. Now you have to make a choice. Are you a partisan of momentum space or coordinate space? If you like coordinate space, here you will have a hard life.
Thank you, Damiano.